so here's what we got. Our goal for part A is to let R be the region in the first quadrant bounded by the graph y equals 2 square roots of x. So I know that function is y equals 2 square roots of x. We're bounded by the horizontal line y equals 6. And then the y-axis. Find the area of R. So I know I'm not going to have enough room to do everything I need to. So I need to find the area of the region. Well, this is the area between the two curves. And I'll tell you right away, there's more than one answer. You could do this with respect to the x-axis, so using dx, or you could do it with respect to the y and get the same answer. So I'm going to do the x-axis with respect to x, so I'll go from, when I break this down, I'm going to go from x equals 0, that's the y-axis, to the x value here, which is x equals 9. So my area with respect to x goes from 0 to 9. And then I have two functions. I have the top function and the bottom function. And anytime we find the area between two curves, it's the top minus the bottom. Well, the top function is just the line 6. Right? And some people are like, well, doesn't that have to have an x in it? Technically, it does. If I put a 0x, that's still in terms of x. That means there's a 0 slope, but the 6 is referring to the x from left to right. And then we're going to subtract the bottom function, which is already written with x in it, dx. You have to show that setup. You can't do any type of work in your head. You have to show this integral. Now, if you set up the y one, you could do that as well. And I'll show you the y value setup, but I won't go through that whole answer. But now we're at the point where we're going to take the antiderivative. Do remember that another way to write the square root of x is x to the 1/2. So you could write that as well. But I'm going to take the antiderivatives now. So the antiderivative of 6 is 6x. If I take the 1/2 and I add 1 to it, that's the 2 over 2. So I'll get an x to the 3/2 up top. But then I'm going to have to put a 3/2 out in front, or excuse me, a 2/2 out in front, and it's going to times by that 2. So that'll be a 4/3. If you can't see what I did there, I had the 2 originally, and then I wrote, if I put a 3/2 up in front, I put a 2/3. 2 times 2 divided by 3 is 4/3. So that's the antiderivative. And then we no longer write the integral symbol. We put the bar in the back. So really focus on notation. If you accidentally, I'm going to erase this, but if you accidentally wrote this again, that's wrong. You wouldn't get full credit because that is not a true statement. That tells you to take the antiderivative again. Yeah. Ooh. It shouldn't. It should be negative. It's a subtraction. Thank you. So I would not have received full credit for that. I know you're shocked that I made an error. It happens all the time. And now we got to evaluate it from 9 to 0. You do not have to show the 0 because when I plug 0 in for x, everything is going to be 0. So you could skip that part. And then we get 54 minus, and this is where I hope you guys can do some of this in your head now. I'll show you what I'm thinking in my brain. I've got 9 to the 3/2 power. So I'm thinking of it as 9 to the 1/2, which is the same as the square root. So 9 to the 1/2 is the square root of 9, which is 3. And 3 to the 3rd power is 27. So I have 27 times 4/3. But then 27 divided by 3, tells me I've got 4 times 9, which is 36. And I do hope you could do that in your head, and if not, then you can do it as side work. Okay, but you don't need to show any of that work right there. And then when I subtract, is that 18? And there you go. So if you if you chose to do it with the y direction, you still should get the same answer of 18. What would that setup be if you chose to do it with respect to y? Okay. So if I did the y value, now I'm going to go from 0 in the y direction up to the highest y value, which is 6. And then I only have the blue function, but it has to be written in terms of y. So I'd have to solve this expression for y. So I'd get 1/2 y equals the square root of x, and then I would square each term, so I would get 1/4 y squared equals x. And then you could move the 1/4 out and work through it. You should get the exact same answer. All right, part B. I might shrink some of this so I actually have more room to work. So let's look at part B. Part B says, write but do not evaluate an integral expression that gives the volume of the solid generated when r is rotated about the line y equals 7. So I'm going to draw a quick sketch. We know that's 6. If I have the equation y equals 7, and I rotate this up, I have a straight line here. This will be 6 units, so this would be at 8. And then 6 units up from 8 is 14. Not a great picture. If I rotate it, hopefully you guys can see that this is a washer problem. This is nice because this helps us review the stuff we've been learning anyways. Notice how my washers are going to stack. If I drew more washers in, they would stack from left to right. So they're stacking in terms of the x-axis. So I'm going to go from 0 to wherever this ending point is, which was 9 on the graph. Then I just need to think of my cross-section here of what's the big radius minus the small radius. It's not easy. So what is the big radius? Well, the big radius goes from the y equals 7 line straight down to this function right here. Now what do we know? We know that the entire length from the red dotted line down to the axis is 7. Okay? But I don't want that. I know that from the x-axis up to this curve, that is the equation 2 square roots of x. So what I'm really looking for is what is the large radius here. What?
Would this afternoon be a better time to take students?
Yeah, probably.
Okay.
That'd be
I'll
great.
come back then later.
Okay.
Thank you.
Yep. So do you guys see how the big radius is 7? The small blue chunk is the equation, because that gets us right to the function. So then we need the red part, which is just the big equation of 7 minus the function itself. So when I subtract those, the red large radius is left over. And then if I do the small radius, what is the small radius? If I go from the dotted line to the line y equals 6, that's the difference between 7 and 6. So that radius is 1. And then we know that the area of a washer is the large radius squared minus the small radius. In my mind, that's the hardest part, getting to that point. Because now, everything else is volume. And volume is the accumulation of area. So, I'm going to start at 0. That's where my first washer would appear. We're going to stack from left to right all the way to x equals 9. I pulled pi out. And then all they total, and I could just write this as 1, because 1 squared is 1, or you put the squared, and then we're stacking from left to right. So that's my deal. And they said write and do not evaluate. It's really important that you see that, because you don't want to spend time trying to solve this. That's a waste of your potential estimated 15 minutes that you should spend on it. All right. So we kind of mentioned this was an AP question. How would they grade these two parts? Well, let's look at just part A quick. Part A is worth 3 of the 9 total points. You got 1 point for the correct integrand, which is the 6 minus 2 square roots of x. Or if you did it in terms of y. If you set it up in terms of y, you would also get that point. You got 1 point for taking the correct antiderivative. So whatever, even if you wrote this incorrectly, if you wrote it incorrectly but then had the correct antiderivative for your point, you could still earn this 1 point, even if you got the first part wrong. Which is important to just say, try something. If you don't know how to start a problem, write something down and do what you think comes next and just try to get 1 point, because that could be really helpful. And then the answer of 18. And again, if you did this in terms of y, if you followed those same steps in terms of y, you get the same answer, you'd still earn those same points. For part B, this was worth 3 points. And if you did our expression, having the large radius squared minus the small radius squared, that was equal to 2 points. I'm not positive on this, but I'm pretty sure they probably give you 1 point for the large radius and 1 point for the small one. They're not super detailed how they do that. Now notice, they wrote theirs a little bit different than ours, which is fine. You can have different expressions and it's equal. As long as it's equivalent, you can still earn those points. So anyways, you get 2 points for those pieces. And then if you have the correct limits and constant. Now what do they mean by constant? Well, your limits go from 0 to 9. You had to have the pi. If you didn't have pi, you're eliminating the area of the circle, which has pi r squared in it, or the area of the washer. So, anyways, 6 out of the 9 points right there. Maybe your confidence level is fairly high for this problem. If not, we're still practicing this, and that's not a bad thing. Okay, so what is our big idea? And actually, a little bit of sad news. There's tissues here if you do need it. Today is my last day. I know. It's my last day of teaching you guys new material. So we are learning the last new material today. Sorry. That's one of my favorite things to do.
So mean. I thought you were going to say, I'm not working here anymore.
No. So this is the last new stuff, which means everything after today is going to be review and building upon and strengthening your knowledge and skills. And so it's really important that you put a strong effort all the way up till May 24th. After May 24th, we get to relax. So what's our big idea of this whole unit? Volume is the accumulation of area. It's a washer or a disk that has been added up. So it's the area of a cross-section. Well, what if we don't have a rotation? What if I can't create a washer or a disk, but I still have a solid? Can I still find the volume of the solid if it isn't made of circles, if it's not made of washer? So, here's our idea. You don't obviously have to write this part. But what if we don't revolve a solid around a line? What if we have something that is projected up from an area? All right, so let's take a look at this. You see the red function here, and I think I can rotate this a little bit. So if you see the red function and blue function, that's the area between a curve, right? And maybe I'll do it this way. And what we can do is, instead of finding a rotation of this, what if an image is projected up from this? So watch this three-dimensionally. There we go. What if a square pops up off of that? So you guys see how the square is created between the area and the length of the square? This is really important. The length of the square is the difference between the red function and the blue function. Right? So it's, remember how we found the area between the curve? Well, that length is a square. Well, what happens now if I increase the amount of squares? What does it create? Now notice the squares are different sizes depending on the movement across the x-axis. So right now we're perpendicular to the x-axis. If I create more squares, eventually I have an infinite amount of squares. What does that turn into? It turns into a solid. Right? Now, that is clearly not a rotation because this is not a cylindrical piece. And if I took a cross-section out of it, it's not a washer or a disk. However, area or volume is the accumulation of area. And what did we accumulate for this example? We accumulated the area of each one of these squares, and the integral adds up the infinite amount. So how else is it going to change today? Well, maybe it's not squares. Maybe it's an equilateral triangle. We can find the area of that. Or maybe it's a semicircle. If it's a semicircle, you can see kind of what that solid looks like. So, visually, this is what we're doing today. We're accumulating a bunch of different shapes, squares, triangles, maybe rectangles. And we're going to start with this. So, I'll give you a second to jot this down. A solid is formed by cross-sections perpendicular to the x-axis. And it's key to understand the x-axis, because sometimes we could do it with the y-axis. And the cross-sections are going to be between these two functions. And if I graphed the value with the positive square root, that would be the red function going above the x-axis. The one with the negative square root is the one below, and together they form a perfect circle. I believe in pre-calc, you guys studied the equation of a circle. X squared plus y squared equals the radius squared. That's where this came from. And we could investigate that, but we're not going to. And then the directions are telling us to find the volume if the cross-sections are blank with the xy plane. So what if they're squares? We're going to do the exact same example. We're going to do it with squares, and then we're going to do it with equilateral triangles, and we'll do it with isosceles triangles, and you're going to notice a little review of geometry here. I'll give you a minute to finish. Okay, so now we need to think three-dimensionally. If the cross-sections are squares, and we are perpendicular to the x-axis, that means you're going to just draw a couple of points. We're going to create a square using that as a sideline. Now, what we're picturing is this three-dimensional square pop up off the page. And we can't draw that super accurately, so we kind of draw it. That's not great. That's not bad. That's horrible, actually. It's going to get a little better. And I know it's hard to tell that these lengths are the same. That's a square because it tells me it's a square. And then there would be more. Right? If I pick another random point, there would be a larger square coming three-dimensionally up off this page. And there would be an infinite amount of squares stacking up from -1 to 1 on the x-axis, or along the x direction. So it doesn't matter how many you draw. You could technically only draw one and get the idea of it. But what we want to do is we want to know that this length is the side of the square. And we got to think back to geometry a little bit. If volume is the accumulation of area, then I need to come up with the area formula for our square. And since it's a square, the area is just whatever that side length is squared. That's true for any square. Anytime you have a square, if you know the side length, you square it. So the big question then is, what is the length of that side? Not a number. That's where you have to really understand what we have here. How long is it from this green, from the x-axis up to the top function? What is the top function? Top function is the square root of 1 minus x squared. So that's how long that green segment is. And here's where it gets a little tricky. When we talk about length, length isn't negative, length is positive. So this length from here to here is the exact same thing as the length from here to here. Because length is always positive. That's why we didn't use the negative value. So my question to you is, how long is the full side length of the square? 2 of those square roots of 1 minus x squared. That's the big idea today. So how do we feel on that? So
Where does the negative square root of minus x squared come from?
where does this come from?
Yeah.
That's the graph of the blue function. So if you were to graph these two in your calculator, that's how you get a circle. Because technically a circle is not a function, so we couldn't graph it without splitting it up as a positive square root and negative square root. But the important thing here is when we talk about length of a side, if I'm going up or I'm going down, it's always positive, which is how long is it. So we are double the length of this green distance, so I've got a square root of 1 minus x squared, double. So, if volume is just the accumulation of the area, then all I need to do is take the area, which is the side length squared, and we know the side length is 2 times the square root of 1 minus x squared. And I should mention, or I should ask you, how come this is dx? And how come this is x? We are stacking squares from -1 to +1 in the x direction, and we are perpendicular to the x-axis. So whatever you're perpendicular to, that's your value, x is in this case. So then where are the bounds? We start at -1. That's where the first tiniest ever square you could ever imagine would appear. And we end at +1. We stack all of those from left to right. Now, we don't have time to do this by hand. Actually, we probably could. Let me show you. You don't write this because you can grab your calculator and do it. But usually students get confused on this first step. So if I didn't do this by hand, or excuse me, if I did do it by hand, you would square each piece, and this would turn into 2 squared is 4, square roots squared is just the individual piece, and then it's much friendlier after that. So hopefully you guys see the algebra step that you would need, and you could either float the 4 out or distribute, and you could do this by hand. But let's just grab our calculator. And I had these all preset. Did you get 16/3? If you do get a decimal, we don't like decimals, so you always want to try to turn it back into a fraction if possible. Sometimes you can't. Okay. So let's take this exact same information, and now, instead of a square popping up, we're looking at equilateral triangle. So, you want to get really creative with it. It doesn't look equilateral because it's drawn kind of an awkward 3-dimensional shift. But now you have triangles popping up. And I'm just using tick marks to indicate that it's equilateral. Here's a nice thing to notice. Did our side length change? We're still spanning this length right here. So my side length is the exact same side length it was in the example above, which saved us a whole lot of time. But the challenge now is coming up with the area formula for an equilateral triangle. And this is honestly more of a geometry problem than it is a calculus problem. So most of my work here is going to be setting up the area formula for the equilateral triangle. And I'm going to think of this as all side work over here. Let's go back to geometry for a little bit. If I have a side length, remember, these are 60-degree triangles, or angles, right? All 60. But the area formula for a triangle is 1/2 the base times the height. So I need to figure out, I know what the base is. The base is whatever the side length is. But what's the height? Now, this is where it gets a little interesting. Remember 30, 60, 90 triangles? And we had something like x, 2x, x squared 3. So the height is half the value of the side, because notice this side is really the same as the 2x. So if I cut the side length in half and times it by the square root of 3, that will be the height. So the height is 1/2 the side length times the square root of 3. I know it's not awesome. But if we do this work once, then you'll have a generic formula for the equilateral triangle. So let's just look at the area now. If I know what technically the base is the side length and the height is 1/2 the side times the square root of 3, it's still a triangle. So 1/2 base times height. The base is what we call the side. And the height was 1/2 the side times the square root of 3. And then we just kind of can combine some like terms because we have multiplication. So the area for an equilateral triangle is 1/2 times 1/2, or 1/4. The side length squared times the square root of 3. And that is the area of an equilateral triangle. I know that might not have been fun, but it's a lot easier to do it this way generically, because now all you have to do is say, well, what's my side? And plug it in there. It's a lot harder to do this every single time when your sides are changing. So you want to make sure you have that just written somewhere.
Once you plug in the side, is that done with
The area. Yep. Because we did all this work. So there's at least some reward at the end. All right, so 1/4 the side squared times the square root of 3 will give me the area. 1/4 the side length squared times the square root of 3. And what is our side? 2 times the square root of 1 minus x squared. Now you could clean this up. It actually cleans up a little better than you think. You could square the 2 and square the square root, and then clean some things up. I'm not really concerned about that today. I want the volume, which we know still goes from -1 to 1, because that's where my first triangle starts and my last triangle goes, from -1 to 1. And then it would just be, you could pull the 1/4 out. Any constant you could pull out. But if you're just writing it and you have it like this, leave it. You don't get any extra points for writing it in a really nice, friendly notation. So that will give me the volume of everything added up. And then we can check that in our calculator. I would double and triple check that I typed in everything accurately. Be like 2.309. If you didn't get that, here's usually the spot that kids make a mistake on. It's this parenthesis and then that square. You have to group the 2 with the square root. So be really careful on that. Grouping symbols are super important. Okay. same question, but what if I told you now it's a right isosceles triangle? And then they tell us where the hypotenuse is located. So they unfortunately they do have some questions like this on the AP test, and they're very tricky. So we're going to draw an isosceles right triangle, and the hypotenuse is the one that's on the x-axis. So isosceles has to have two congruent sides, and then it's a right triangle, and you can see the hypotenuse lies on the perpendicular to the x-axis. Now you can draw as many of those as you want, right? We're accumulating the area. But the big thing is, we just need to know the side. And that's what we have already. The side is double the length of this equation. And since I don't have that on the screen, I'm just going to rewrite it. Now we got to go to area of isosceles. So we're going to do more side work. You don't have to draw it in that direction. This is just kind of generally speaking. But what if I know the hypotenuse? I just call it my side. Here's where it gets a little tricky. I don't know this side or this side. I could call it A and B because I'm thinking Pythagorean theorem here, but it's isosceles. So if that side is A, then this side is A. So what does that mean? It means A squared plus A squared would have to equal our side length squared. And you don't, I should say this, you don't really actually have to write all this unless you want to. All you need to know is once we have a isosceles right triangle, what's the equation for? But it's good to know that it comes from somewhere. So A squared plus A squared is 2A squared. And that's equal to this side squared. And then my goal is to figure out what is the length of A, right? Because that's the base and the height. So I'm going to solve for A. So I'll get 1/2 side length squared. And then I'll take the square root. And we could algebraically break that down more if we wanted to, but we don't really need to right now. I'll slide this down. So then I want the area of that triangle, which is 1/2 base times height. Well, in this case, because it's an isosceles, the base and the height are the same thing. So if I multiply these two together, isn't that the same as squaring it? So I could actually write this even better. 1/2, and when I square a square root, don't those cancel out? So the square root's going to go away. And then 1/2 times 1/2 tells me anytime I have an isosceles right triangle and its hypotenuse lies on the section. Here's my formula. Well, we know what our side length is now, so I could set up the area and then set up the volume. You really don't even need to draw this area out. And again, if we were doing this by hand, I would square each piece here, and this would be a 4, which would reduce the 1/4 out. And then the square here would get rid of the square root, and you would really be left with, that is your area. Much friendlier, you can totally do this by hand. Right? So then our volume, -1 to 1. And this answer should be the exact same thing as if you just plugged this area into the integral as well. Because algebraically they're equivalent. So again, I hope you could do that part by hand. Just to save us time, I'll tell you the answers 4/3. Most likely, this would be a no calculator problem. Because once you get the area, algebraically it breaks down to this right here. And that's a really friendly antiderivative. You can take it each week. I know it's not fun to do, but... Alright, last one. What if it's a right isosceles triangle with one leg perpendicular to the x-axis? What would that picture look like? Well, it's a random spot perpendicular to the x-axis. There's the side line. And then it's a right triangle where a leg is on there. It's a right isosceles. So this length will be congruent with that one. And again, these pictures aren't drawn perfect. But you know the side length already. This side length is 2 square roots of 1 minus x squared. So then I just need to find the area for the right isosceles. But this time it's different because they give us a leg, which is not bad at all. This is actually really friendly. We probably don't even need to do side work for this one. Because what do we know? Each leg is the same, and that's my base. And that could be my height. So technically, if the base and the height are the same thing, you could just square it right away, right? If you want a formula, some people like it. If it's that case, it's just your side length squared times 1/2. And we didn't have to generate that, that just kind of naturally came up. So if I was to FOIL this or square it, I would get 2 times 2, which is 4. And I get the square root times the square root, which gets rid of the square root. And then half of 4 is 2. And you could stop there, you could distribute the 2 if you want. But here's my area expression for that triangle. And then the volume is just the area evaluated from -1 to 1. I thought we were going to get to one other example, the third part of that free response question. We don't have time, which is completely fine. We can do that. We'll do that next week, just as a nice review. But what if I told you, you don't have to write this, because this one is pretty decent. What if I told you that's a semicircle, which apparently is hard to spell. So, what if I had a semicircle coming up over the top? The area formula, what's the area formula for a semicircle? Perfect. IR squared sounds like area to me, but if it's a semicircle, you have to put the 1/2. Now the only question here then is, what is my radius? The radius is not the same as the side length we had for all the other problems, because the radius is half that value, so it's just the square root of 1 minus x squared. And that's just, then it would be the same work, do the volume, the integral of the volume from -1 to 1. So, I had plenty of examples. We didn't get through them. Here's what we got tonight. I just want to make you aware of where to see this. So I just updated. I realized I didn't have this link in here as of this morning. So our homework tonight is a review worksheet. I will put the answers. I haven't put them up yet. But here is the review. And it's a handful of problems that will help us through the test. Notice this question down here. It's the back side. Part D is optional. And then we do say when you should use a calculator. So like for part A, on number 2, you should use a calculator, but then you shouldn't use it for any of the other parts. All right? And to check your work from today, we're going to take region H, and we're going to look at squares, equilateral triangles, isosceles, and semicircles. So that's kind of the practice for today. That's why we didn't have extra homework on this piece. I don't think we need extra homework and then a review. So when it says region H, here's region H right here. You're going to go from, and you'll have to find this intersection point. That's what part A is. So you go from this x value to x equals 9. And then H, we're looking at it perpendicular to the x-axis. So picture the squares. I think I can draw on this? I'm not sure if it lets me. Picture the square coming up off of here, right? Or if they say it's a semicircle, then you're picturing the semicircle. And then you just got to think about, well, what is the side length? And it's based off of whatever this function is, which is described. So, again, the answers will be posted so you can check your work. All right. Also good news, since we got to have 1 minute left, I got confirmation that on May 14th, I'm allowed to have students come in on a Friday and do a practice AP test in here. So I'll email something out, maybe like a Google form, and just get your feedback on if you're willing to come in, volunteer to come in. It would be about a 4-hour time commitment. And I have meetings in the morning, so it'd probably be 11:30 to 3:30. If you guys are okay with that, that's a great opportunity for you guys to get an extra practice test under your belt. So that's all I have. Adios to everybody on Zoom.